This is the second lecture on the topic Motion under Central Forces, which is Unit 13 of BPH CT 131. And in the first lecture, you learnt how to identify a central force. What is a central force? A central force is a force which is always directed towards or away from a particular point which remains fixed. This fixed point is called the center of force, and we write it mathematically as the product of a scalar function multiplied by a unit radial vector. You also learnt what is a central conservative force. When the magnitude of the force depends only on the distance of the object from the center of force, it is called a central conservative force. How do we write a central conservative force mathematically? We write it as the product of a function of r multiplied by the unit radial vector. And it is called conservative because the work done by a central conservative force is independent of the path followed by the particle and depends only on the distance at the endpoints of the particle from the center of force. Now let us move on to understand motion under a central force and under a central conservative force. So basically you know what is a central force, a central conservative force, and you can identify from the mathematical expression of the force whether the force is central or central conservative. So next we want to understand how a particle or an object moves under the action of a central conservative force or even a central force. Now suppose that a particle of mass m is moving under the influence of a central conservative force. We write it as the product of a function of the distance of the particle from the center of force multiplied by the unit radial vector which acts outward from the center of force. So you know how to write the equation of motion. It is the mass times the acceleration is equal to the force, which is Fr into r cap. What is the acceleration? The acceleration of the particle is given by d2r by dt2, where r is the position vector of the particle. So as the position vector changes, you define the velocity of the particle as dr by dt and the acceleration as d2r by dt2. Now you are familiar with differential equations, so you can see that this is a second order differential equation which if you solve you will be able to see how r changes with time. Now that is a complicated process and we will not be doing that here. You will be doing it in higher classes, but right now what I can tell you is that even without solving this equation of motion, there are certain features of motion under a central force which you can identify. What are these features? So basically we are going to look at the general features of motion under central and central conservative forces without going into the solution of the equation of motion. So what do we know about a central conservative force? We know that the total mechanical energy is conserved because it is a conservative force. So basically you know one thing about motion under a central conservative force, and that is that the total mechanical energy is conserved. So what are these forces which are central conservative forces? They are the gravitational force, the electrostatic force, the spring force. These are all forces which conserve the total mechanical energy. Now let us look at another property of a central force. Suppose we have a particle which is acted upon by a central force. Right now I am not specifying that it is a central conservative force. I am saying that it is a central force. So a central force which is defined by the product of a function f multiplied by the unit radial vector r cap. Now the center of force is O, the unit radial vector is r cap. So what is the torque about the point O due to the force F? F is a central force, right? Now you can see that you can write the expression for the torque as the vector product of the position vector and the force. So tau is equal to r cross f. What is r? R is the position vector of the particle, and you know that it is nothing but the product of the magnitude of the distance of the particle from the center of force multiplied by the unit radial vector. So basically r is nothing but the magnitude of the distance multiplied by the unit radial vector, and the central force anyway is a scalar function multiplied by the unit radial vector. So the torque due to the central force can be written as R into F into the vector product of the unit radial vector with itself. So what can we say about that? Now you know that the vector product of two identical vectors is always 0. Why is that? Because the magnitude of a vector product is the product of the magnitudes of each of the vectors multiplied by the sine of the angle between them. If we have two identical vectors, the angle between them is 0 and sine 0 is 0. Therefore, we can say that as true for the vector product of any two identical vectors, the vector product of the unit radial vector with itself is also 0. So this is nothing but the null vector. So what do we know? Now we know that whatever be the type of central force, provided it is a central force, the torque due to the central force about the center of force is a null vector. So the torque due to a central force about the center of force is always 0, and as I have said, this is true for any type of central force and not just a central conservative force. In Unit 12, you have studied the dynamics of rotational motion and you know how to connect the torque to the angular momentum. So the torque due to a force about a point is equal to the rate of change of angular momentum about that point. So now if I say that the angular momentum of the particle is given by L, L is the angular momentum about the center of force, tau is the torque about the center of force. Now as we have already shown that for a central force the torque is 0, this means that the rate of change of angular momentum is also 0. What does that tell us? That tells us that because the net torque due to a central force is 0, the angular momentum of the particle about the center of force is also constant. So the angular momentum L is constant, and remember that this is true for any type of central force and not just a central conservative force. For any central force, the torque about the center of force is 0 and the angular momentum is a constant. So the angular momentum is conserved for a motion under a central force, be it conservative or not. Now, how do you define the angular momentum? You know that if the position vector of a particle with respect to a point is r and its momentum is p, then angular momentum is defined as the vector product of r and p. If v is the velocity, then you can write the momentum p as just the product of the mass m into the velocity. So basically the angular momentum is r cross mv. M is a scalar quantity, so we are interested in the vector product of the position and the velocity of the particle. The angular momentum is going to be directed at right angles or perpendicular to the plane containing the position vector and the velocity vector. Now suppose now we consider a particle moving and the position vector at any particular point is r and its velocity at that point is v. Let us define a plane that contains these two vectors r and v. So the angular momentum is going to be directed perpendicular to this plane. So basically L is perpendicular to the plane containing r and v, that is, it is perpendicular to the plane in which the particle is moving, because r and v define the motion of the particle. So O is the center of force, r and v are the position and velocity vectors, and the angular momentum about the center of force is at right angles. We have also shown that L is constant and that means it is constant in magnitude and direction. So the angular momentum is always going to be in a fixed direction. That means that because the angular momentum is in a fixed direction, it is and since it is always perpendicular to the plane containing r and v, that also means that the plane containing r and v is fixed. So basically we can say that for a central force, because the angular momentum is a constant of motion, the plane containing r and v is also fixed, and this is at right angles or perpendicular to the angular momentum. This is true for any central force and not just a central conservative force. So we can say that for a central force, a particle always moves in a fixed plane which is perpendicular to the direction of its angular momentum. This is a special property for the motion of a particle under a central force. So even without solving the equation of motion of the particle and moving under a central force or a central conservative force, what are the two things, important things that you know about this motion? You know that for a central conservative force, for motion under a central conservative force, the total mechanical energy is a constant, the angular momentum about the center of force is constant, and that means it is constant both in magnitude and direction. And because the angular momentum is fixed in magnitude and direction, the particle always moves in a plane perpendicular to the direction of the angular momentum. For motion under central forces which are not central conservative forces, what can we say? We say that the angular momentum is constant in magnitude and direction. The angular momentum is about the center of force, and even for central forces which are not conservative, the particle will also move always in a plane perpendicular to the direction of the angular momentum. So what are the constants of motion for central conservative forces? For central conservative forces, the constants of motion are the total mechanical energy and the angular momentum about the center of force. Angular momentum is a vector quantity, so when I say angular momentum is a constant of motion, I mean that the direction and magnitude of the angular momentum is fixed. On the other hand, for a central force, only the angular momentum about the center of force is fixed. Now a little more detail about the motion under a central force, but before we talk about that, let us now discuss something called general angular motion. What do I mean by general angular motion? To understand that, let us first look at something you have studied in great detail in Unit 11. In Unit 11, you studied angular motion with particular reference to circular motion. You studied two types of circular motion, uniform circular motion and non-uniform circular motion. Now, in circular motion, the particle moves in a plane, and I have shown that this is the xy plane. At each point of its path, the particle is at a fixed distance from the center of the circle, and the velocity is always directed at a tangent to the path. So, the angular speed for uniform circular motion is constant. That is, it covers equal angular displacements in equal intervals of time, and the linear velocity, which is connected to the angular velocity by the relation v is equal to r omega, where omega is the angular speed, is also a constant. Omega is constant, omega is d theta by dt, and v is also a constant because v is equal to r omega. Omega is constant and r is also constant for circular motion. The next thing we studied about was non-uniform circular motion. What is non-uniform circular motion? In non-uniform circular motion, you have an angular speed that is changing. So basically, you have the rate of change of angular velocity, that is d theta by dt, equal to the angular acceleration. So angular acceleration alpha is d2 theta by dt2. Now because v is equal to r omega and omega is changing with time, we also have that the magnitude of the linear velocity v is changing with time. So basically, the difference between uniform and non-uniform angular circular motion is that in uniform circular motion, omega and v are constants. In non-uniform circular motion, omega and v are changing. Okay? But remember that because it is circular motion, r is not changing with time. The distance of the particle from the center of the circle is always fixed, and v is also always directed along the tangent to the circle. In contrast, we define something called general angular motion. What is general angular motion? Suppose you imagine that a particle is moving in a plane, but it is no longer moving in a circular path. Let us say that it is moving in an elliptical path from the x-axis towards the y-axis. This path can be anything, but let us imagine that it is part of an ellipse. Now, let us consider any 2 points P and P prime. The position vector of the particle at the point P is r, at the point P prime it is r prime, and the velocities, the linear velocities are v and v prime. The angular displacement relative to the x-axis are theta and theta prime. So, what do you see? As the particle is moving, not only is theta changing with time, but the distance of the particle from the center or the origin is also changing with time. So, in general angular motion, in contrast to circular motion, either uniform or non-uniform, the distance of the particle from the center or the origin changes with time. So, basically both r and theta vary with time. So, when you talk about the rate of change of theta, that is d theta by dt, in this case you must also talk about the rate of change of r with time, which is the rate of change of the distance from the origin with time. Now, before we describe the details of angular motion under a central force, let us talk about a type of coordinate system that we use to describe angular motion, and in particular this is used to describe general angular motion. Now, let us look at the familiar first, let us look at the 2D Cartesian coordinate system. Now, you are familiar with this from your school days. You have the x and y axes at right angles to each other, and you locate a point in the plane. Remember, the xy, this is the xy plane. You locate the point P. Its position is located by two coordinates x and y, which are shown in the figure. Now, suppose I want to look at another way of locating this particle. One way is by defining its x and y coordinates. Let us say that I want to define the position of the particle in terms of the distance of the particle at the point P from the origin, that is, I call this distance r, and I use another coordinate which is the angle that OP, which is the distance of the point from the origin, makes with the x-axis. So, basically now instead of using the two coordinates x and y to describe the position of the particle in the plane, I am using the coordinates r and theta. So, r is the distance of the point from the origin, theta is the angle that the line OP, which is the line joining the particle to the origin, makes with the x-axis. So, the equivalence between the two coordinates are that x and y are replaced by r and theta. R and theta are called the plane polar coordinates of the particle or the point P. Now, how do you relate the Cartesian and the plane polar coordinates? Now, let us look at the figure clearly. Now, OP is r. The distance between if you drop a perpendicular to the x-axis, this distance is defined by x. If you drop a perpendicular to the y-axis, this distance is y, and the angle that OP makes with the x-axis is theta. So, this is a right angle triangle, and you can see that you can write x is equal to r cos theta and y is equal to r sin theta. So, this is the equivalence between the x and y coordinates and the r theta coordinates, which are the plane polar coordinates. X and y are the two-dimensional Cartesian coordinates. So, now let us say that we also want to define unit vectors. You already know that in the Cartesian coordinate system, the unit vectors for the 2D Cartesian coordinate system will be the I and j vectors, which are along the x-axis and the y-axis, and irrespective of where the point is located in the xy plane, we know that these two vectors remain unchanged. Now, instead, let us define a set of vectors r cap and theta cap. Suppose r cap is the unit vector along the line that joins the point to the origin, and theta cap is a unit vector which is at right angles to this unit vector r cap. So, now we have, instead of I and j, we have two unit vectors r cap and theta cap, and you can see for yourself that as the point is located, when the point is located in a different place, the direction of r cap and theta cap are going to change. So, unlike I and j, which always have a fixed direction, r cap and theta cap will change depending on the location of the point in the plane. So this is the difference in the unit vectors I cap and j cap and r cap and theta cap. Theta cap is a unit vector in the direction of increasing theta, and r cap is a unit vector in the radial direction. So suppose a particle is located at this point P, which is defined by the coordinates x and y. How do you write the position vector r in terms of the unit vectors I cap and j cap? You say that r is equal to x I cap plus y j cap. Now, if you want to define the position vector in plane polar coordinates, you can see for yourself that the position vector r, it is the same vector, is nothing but the magnitude of r multiplied by the unit radial vector. So, r vector is equal to magnitude of r multiplied by the unit radial vector. This is how you represent r in either the Cartesian system, 2D Cartesian system, and in the 2D plane polar coordinate system. How do we define these unit vectors? Now you already know that the vector, position vector in the Cartesian coordinate system in a plane is written by as x I cap plus y j cap, and because you know that x is equal to r cos theta and y is equal to r sin theta, then we can write the position vector also in terms of r and theta as equal to r cos theta I cap plus r sin theta j cap. Now, what is the unit vector in the radial direction? The unit vector in the radial direction is just the position vector divided by the magnitude of the position vector. So, you can see that if you divide r vector by the magnitude of r vector, then that is nothing but r cap r vector by r is equal to cos theta I cap plus sin theta j cap, which is nothing but the unit radial vector r cap. So, r cap is equal to cos theta I cap plus sin theta j cap. So, what have we done here? We have expressed the unit radial vector in terms of the Cartesian coordinate unit vectors that are I cap and j cap. Now, you can work out for yourself that a unit vector perpendicular to the unit radial vector is given by minus sin theta I cap plus cos theta j cap, and this is how we define the unit radial vector in the direction, unit vector in the direction of increasing theta. So, theta cap is equal to minus sin theta I cap plus cos theta j cap, and r cap is equal to cos theta I cap plus sin theta j cap. Right now, so far we have discussed the plane polar coordinates and the unit vectors in the plane polar coordinate system, and in the next lecture we will study how we can describe velocity and acceleration in plane polar coordinates. So, let us briefly summarize what we have studied in this second lecture on the topic unit. So, in this lecture we studied the properties of motion for motion under central and central conservative forces. The angular momentum about the center of force is constant in magnitude and direction. This is true for both central forces and central conservative forces. Therefore, a particle on which a central force is exerted moves only in a plane perpendicular to the direction of its angular momentum. For motion under central conservative forces, the total mechanical energy is a constant. So, for central conservative forces, both the total mechanical energy and angular momentum are constants of motion, but for central forces, the constant of motion is just its angular momentum. Thank you.